This is Lesson 20 in our Calculus 1 series, Curve Sketching. So far we've learned that when f prime of x is positive, f is increasing, and when f prime of x is negative, f is decreasing. We've also seen that f double prime of x positive means f prime is increasing, and so f is concave up. Similarly, f double prime negative means that f prime is decreasing and f is concave down. In this lesson, we use this information to help us sketch the graphs of functions. So here are our steps for curve sketching. We want to first find the domain, then find and plot any intercepts and asymptotes on the graph, find and plot any relative extrema and find intervals of increase and decrease, find and plot inflection points and find intervals of concavity, and then sketch. So let's take a look at an example. Use calculus to sketch the graph of y equals x to the fourth minus 6x squared plus 8. The first step is to find the domain, and here we have a polynomial, so we know the domain is all reals. Then we're asked to find intercepts and asymptotes and plot them. For intercepts, we take a look at our y-intercept by setting x equal to 0. Setting x equal to 0, we have y equals 0 to the fourth minus 6 times 0 squared plus 8, and so that's 8. That tells us the point 0, 8 is on the graph. For our x-intercepts, we set y equal to 0, and we have 0 is equal to x to the fourth minus 6x squared plus 8. Factoring here, we have x squared minus 4 and x squared minus 2. Setting both of those equal to 0, we get x is equal to positive or negative 2, or x is equal to positive or negative radical 2. So our x-intercepts for the graph are positive or negative radical 2, 0, positive or negative 2, 0. And notice we have a polynomial, so we know that there are no asymptotes for this graph. So now we need to plot our intercepts, so let's do that. And so we're here. Continuing, we want to find relative extrema and intervals of increase and decrease. So our original function is x to the fourth minus 6x squared plus 8. We find our derivative, 4x to the third minus 12x. We notice that it always exists, so the only critical numbers would come from the derivative equaling 0. We factor here, we factor out a 4x, and the remaining factor is x squared minus 3. And so we set 4x equal to 0 and x squared minus 3 equal to 0, and we get x equals 0, or x equals positive or negative radical 3. Now, to find intervals of increase and decrease in any relative extrema, we have to put these numbers on a number line and find the sign of y prime on the intervals. So I like to use the factored version of y prime for these evaluations. So y prime is equal to 4x times x squared minus 3. Here we could use a negative radical 4, which would be x equals negative 2. Y prime of negative 2 would be a negative 8. And then we'd have negative 2 squared, which would be 4 minus 3, so that would be a positive, and this would be a negative product. So we have a negative sign here. Here we could use negative radical 1, which would be x equals negative 1. Y prime of negative 1 is going to be negative 4 multiplied by negative 1 squared, which is 1 minus 3. So this factor is negative, and then we have a positive product. Here we can use x equals positive 1. Y prime of 1 is going to be positive 4, and then 1 minus 3 on the inside, so that's negative. So we have a negative product. And then say x equals 2 out here, y prime of 2 is going to be 4 times 2, that's positive, and then 2 squared minus 3, that's going to be also positive. So this is a positive product, and we're here. So what does that say about the original y? It says that y is decreasing, then increasing, then decreasing, then increasing. Decreasing, then increasing gives us a relative minimum. Increasing, then decreasing gives us a relative maximum. Decreasing, then increasing gives us a relative minimum. So we have y increasing on negative radical 3 to 0, union radical 3 to infinity, and y decreasing on negative infinity to negative radical 3, union 0 to radical 3. We have relative minimums at x equals radical 3 and negative radical 3, but we should find the corresponding y values to go with these x values, especially because we'll be plotting them. So let's go back to the original and plug in positive and negative radical 3. Because we have even powers only here, it doesn't matter if we're looking at positive or negative radical 3, we'll end up with the same y value. So that's going to be radical 3 to the 4th is going to be 9 minus 6 times 3 plus 8. So that's 9 minus 18 is negative 9 plus 8, that's a negative 1. So these y coordinates here are both negative 1. And we have a relative max at x equals 0. That point is already plotted on our graph because it's one of our intercepts, right? That was 0, 8. So now that we have the intervals of increase and decrease and the relative extrema, we need to plot these extrema on our graph. So our relative max is 0, 8, and that's already plotted. That's here, that's our maximum. And we have radical 3, negative 1, negative radical 3, negative 1. Okay, so now we know that 2 is radical 4, so radical 3 needs to be somewhere in between here. So that'll be about here. And similarly for negative radical 3, and so negative radical 3, negative 1 will be about there. So we know that our graph is going to be decreasing. It's going to go through this intercept, hit this minimum, go through this intercept, and then have a relative maximum here, then go through this intercept, hit the minimum, intercept, and then increasing again. So we already have an idea of what this graph looks like. And we didn't even talk about inflection points and concavity yet. And this generally happens after you find your relative extrema and intervals of increase and decrease. You can generally get a basic graph of the function at that point, and then you go back and find your intervals of concavity and inflection points and just fine-tune your graph. So let's continue here by taking y double prime and looking at inflection and concavity. Y prime is 4x to the third minus 12x, so y double prime is equal to 12x squared minus 12. This always exists. And so any potential points of inflection would only come from f double prime equaling 0. So we set this equal to 0 and factor, and we get x equals positive or negative 1. So we put positive and negative 1 on a number line and find the sign of y double prime on each interval. Y double prime is equal to 12 times x squared minus 1. So here at, say, x equals negative 2, we're going to have a positive 12 on the outside, and then we're going to have a 4 minus 1, which is positive 3 on the inside. So this is going to be a positive product. Here we can test x equals 0. We're going to have a positive 12 on the outside, and then a negative 1 on the inside, so that's going to be a negative product. And here we can test x equals 2. We're going to get the same thing we have here. We're going to have a positive 12 on the outside and then a 4 minus 3 on the inside. So that's positive as well, and this is a positive product. So what does this say about y prime? It says that y prime is increasing, decreasing, and then increasing. And so what does that say about y? It says y is concave up, then concave down, then concave up. And so we have points of inflection at x equal positive and negative 1. So we should also find the y coordinates to go with those points. Let's go back to the original. Y of positive or negative 1 is going to be 1 minus 6 plus 8, and that's going to be 3. So negative 1, 3, and 1, 3 are the inflection points for this graph. Our graph is concave up, then concave down, then concave up. Let's go back here to our sketch and see if negative 1, 3 and 1, 3 are on our graph, and if they look like they are the inflection points. Here's x equals negative 1 and positive 3, that's about here. And here's x equals positive 1 and positive 3, that's about here. And these are our inflection points. And so our graph is concave up, and then concave down, and then concave up. And that's our sketch. Let's take a look at another example. Use calculus to sketch the graph of f of x equals x squared over x squared minus 1. Again, we want to start by finding the domain. And here we notice that our denominator would be 0 at x equals positive or negative 1. So our domain here is x is not equal to positive or negative 1. In step 2, we want to find intercepts and asymptotes. So for intercepts, we start by taking the y-intercept by letting x equal 0. And so we get y equals 0 square over 0 square minus 1. And so that's y equals 0. And so our graph goes through the origin. And now we want to see if there are any other x-intercepts. So we set y equal to 0. And we have 0 equals x squared over x squared minus 1. A fraction equaling 0 means the numerator is equal to 0 and the denominator is not. So x squared equaling 0 says x equals 0. That's the same point we have here. So we just have an intercept at the origin. Let's take a look at asymptotes. We know that x equals 1 and negative 1 are not in the domain of the function, so let's check to see if we have asymptotes at those values. We have vertical asymptotes when the function evaluation would be non-zero over 0. So if we plug in x equals positive or negative 1, we get non-zero over 0, and so yes, both of those x values give us vertical asymptotes. For horizontal asymptotes, remember we want to take the limit as x goes to positive and negative infinity of our function. And I'm putting negative and positive infinity here because we realize the computation will be the same for the limit. And we start by looking at the highest power we have in the denominator and dividing by x to that power. So we have 1 over x squared here, 1 over x squared. And so this is limit as x goes to positive or negative infinity of 1, now I'm multiplying here, I get a 1 in the numerator, and I get a 1 minus 1 over x squared in the denominator. Now, as x goes to positive or negative infinity, this 1 over x squared is going to 0. So this is going to be 1 over 1 minus 0, which is just 1. So this says y equals 1 is a horizontal asymptote as x goes to infinity and as x goes to negative infinity. So now let's plot our intercepts and asymptotes. So we have our intercept at the origin, we have vertical asymptotes at x equals positive and negative 1, and we have horizontal asymptotes at y equals 1. Now let's take a look at our first derivative and find relative extrema and intervals of increase and decrease. Our function is x squared over x squared minus 1, so our first derivative is bottom times derivative of the top minus top times derivative of the bottom over bottom squared using the quotient rule. So we have x squared minus 1 times 2x minus x squared times 2x over x squared minus 1 quantity squared. We notice that we have a factor of 2x in both terms here, so we can factor that out. And what's left on the inside is then x squared minus 1 minus x squared. And so that simplifies to a negative 1, and this numerator becomes negative 2x over x squared minus 1 quantity squared. Now to find critical numbers, we want to see where this does not exist and where it is equal to 0. We see that this fraction does not exist where the denominator is 0, and that's at x equals positive or negative 1. But these are asymptotes, not critical numbers. They will still, however, go on the number line as we test our intervals. Let's also set this first derivative equal to 0. We notice that happens when negative 2x is equal to 0 or x equals 0. That's a critical number. And so our number line looks like this, so we can test the sign. Remember, f prime of x is equal to negative 2x over x squared minus 1 quantity squared. That denominator is always going to be positive, so we're just looking at the sign of the numerator here. Here, if we take, say, x equals negative 2, we're going to have a positive numerator. Here, if we take x equals negative a half, again, we're going to have a positive numerator. Here we could take x equals positive a half, and that will give us a negative numerator. And here, say x equals 2, another negative numerator. So we have a function that is increasing, then there's an asymptote, then it's increasing, then decreasing, then there's another asymptote, and then it's decreasing. Now with that information, again, we should be able to make a basic sketch of the graph and then go back and check that the concavity is correct. So we have our function increasing when x is less than negative 1. So let's see what we have here. We know that we have a horizontal asymptote as x goes to negative infinity at y equals 1. If we have our graph increasing on this interval, we know it must look like this. Between x equals negative 1 and x equals 1, our graph is increasing and then decreasing. We know it goes through the origin, And we know that it has asymptotes here at -1 and 1, so it must look like this. And we know after the asymptote, our graph is decreasing, and it has a horizontal asymptote at y equals 1 as x goes to infinity, so our graph must look like this. Now let's take a look at the second derivative and just verify that we have the correct concavity. Our first derivative is here, -2x over x squared minus 1 quantity square. So our second derivative uses the quotient rule. Bottom times the derivative of the top minus top times the derivative of the bottom over bottom squared. Again, it's easiest to factor first to simplify, so we factor in x squared minus 1 from both terms in the numerator, and then we're left with x squared minus 1 times -2, and here we have minus a -2x times 2 times 2x, so that becomes a plus 8x squared. So we can cancel a factor of x squared minus 1, and simplifying we're here. We have 6x squared plus 2 over x squared minus 1 to the third. Again, this does not exist at x equal positive or -1, but those are asymptotes of our original function. And now, where does this equal 0? Well, notice 6x squared plus 2 cannot equal 0, because 6x squared cannot equal -2. So there's no solution here, and so the only numbers that we need to put on our number line for concavity are the asymptotes. So we're here, and now we want to test a point in each interval to see the sign of f double prime. So here, for example, x equals -2, f double prime of -2 would be 6 times -2 squared plus 2 over -2 squared, which is 4 minus 1 to the third. We're going to have positive over positive. This is going to be positive. Here we can choose x equals 0. F double prime of 0 is going to be 2 over -1 to the third. So that's going to be negative, and then we have a negative sign here. And for x equals 2, f double prime of 2 is going to be the same thing that we have here. It's going to be 6 times 4 plus 2 over 4 minus 1 to the third, and that's all positive. So what does that say about f prime? It says f prime is increasing and then decreasing and then increasing. And about f, that says f is concave up, then concave down, then concave up. So the first part of our graph is concave up, the middle part is concave down, the rightmost part concave up. And that does match what we have here. Concave up, concave down, concave up. And so that's our sketch. Let's take a look at another. Here we have f of x equals radical x squared plus 1 minus x, and again we want to use calculus to sketch. So we're going to start with the domain, and notice here, because we have a radical, we need to make sure that x squared plus 1 is greater than or equal to 0. But notice this is always true because x squared is always going to be greater than or equal to 0. So our domain here is the entire real line. So that means we're not on a restricted domain, and also we're not going to have any vertical asymptotes. The next step is to find our intercepts and horizontal asymptotes then. So for intercepts, we start with the y-intercept and set x equal to 0. So f of 0 is going to be radical 0 squared plus 1 minus 0. So that's radical 1, and that's equal to 1. So our y-intercept is 0, 1. And to find any x-intercepts, let's set y equal to 0. 0 is equal to radical x squared plus 1 minus x. We can add x to both sides, square. And notice here we have x squared is equal to x squared plus 1. But that can't be true, because subtracting x squared from both sides says that 0 is equal to 1, and we know that can't be true, so there's no solution here. And so there are no x-intercepts. For our asymptotes, we said that because the domain is all reals, we have no vertical asymptotes. But what about horizontal asymptotes? We need to take a look at the function values when x goes to positive and negative infinity. So let's start here with x going to infinity. We notice here that we're going to have infinity minus infinity, which is an indeterminate form. So that means we need more information to compute this limit. So let's rationalize here by multiplying by the conjugate. So our numerator is going to be x squared plus 1 minus x squared. And our denominator now has radical x squared plus 1 plus x. So here we have the limit as x goes to infinity of just 1 over radical x squared plus 1 plus x. And so we have infinity plus infinity, that's infinity in the denominator. 1 over infinity is equal to 0. So we have y equals 0 is a horizontal asymptote as x goes to infinity. Now let's take a look at as x goes to negative infinity. This one's a bit easier because we have negative infinity quantity squared plus 1, that's going to give us infinity under the radical, that's a positive infinity, minus a negative infinity. So that's infinity plus infinity, that's infinity. So that says there is no horizontal asymptote as x goes to negative infinity. So we only have a horizontal asymptote at y equals 0 on the right side of this graph. Now let's plot intercepts and asymptotes. We said our intercept is 0, 1. And as x goes to positive infinity, y goes to 0. So we have a horizontal asymptote here. And that's as much as we know so far, so let's continue. We want to find any relative extrema and intervals of increase and decrease by taking a look at the first derivative. So taking a look at the first derivative, we have 1/2 x squared plus 1 to the negative 1/2 multiplied by 2x, that's using the chain rule here. And then from the minus x, we have a minus 1 here. So this is our derivative. And the first thing we notice is that this derivative always exists because this denominator can never equal 0. And so if we have any critical numbers, they must be coming from f prime equaling 0. So let's set f prime equal to 0. So here we have x equals radical x squared plus 1. And again, we square both sides and we have no solution. We saw this earlier. So that tells us there are no critical numbers. We have no critical numbers and no asymptotes, so that means there's nothing to plot on the number line. That means f prime remains the same sign always here. And so we write down our number line, but we realize that we just need to test any x value in the entire real line, and whatever the sign of f prime is there, that's always the sign of f prime. So I like easy x values, so I'm going to choose x equals 0 and plug that into f prime. Here's f prime, so 0 over radical 0 squared plus 1, that's 0 minus 1. This is going to be negative. That says our function is always decreasing. Now after step 3, we should always have an idea of what the sketch looks like, and then we'll go back and check our concavity. So we know that f is always decreasing. It goes through the point 0, 1, and it has a horizontal asymptote on the right side at y equals 0. So the graph must look like this. Now let's check our concavity to make sure it agrees. Here's our first derivative. So our second derivative, we're going to use the quotient rule here, and we get a 0 from the second term. Bottom times derivative of the top minus top times derivative of the bottom over bottom squared. So to simplify, we want to multiply by radical x squared plus 1 over itself. And so in the numerator, we have x squared plus 1. Here, the 2 and the 1/2 cancel. The radical x squared plus 1 cancels this term, and we just have minus x squared. And in the denominator, here's to the first power plus another 1/2 power, so we have x squared plus 1 to the 3/2 power in the denominator. So simplifying, this is 1 over x squared plus 1 to the 3/2. And we notice that this always exists, and it can never equal 0. So again, we have no points to plot on our number line. That means f double prime is going to be the same sign always. So again, we can test any point on the entire real line and see the sign of f double prime. And so I'm going to choose x equals 0. And here we have 1 over 0 squared plus 1 to the 3/2, that's going to be positive. And so that says f is always concave up. And so now let's go back to our sketch. Does that agree with what we have? Yes, it does. F is always concave up. And so this is our sketch. Now let's take a look at another. Use calculus to sketch the graph of y equals 2x minus tan x on the interval negative pi over 2 to pi over 2. So our first step is to identify our domain, And in fact, that's given to us, this open interval from negative pi over 2 to pi over 2. Step 2 is to identify intercepts and asymptotes. So let's take a look at our y-intercept by setting x equal to 0. That's 2 times 0 minus tan of 0, so that's 0 minus 0, so that's 0. So that means this graph goes through the origin. And let's see if we have any other x-intercepts by setting y equal to 0. When we set y equal to 0, we have 2x minus tan x is equal to 0. Well, that says 2x is equal to tan x. This is not something we know how to solve algebraically. When you encounter something like this, we just move forward, move on. Perhaps there's more than one solution. We know that x equals 0 gives us a solution, but is there another one? We're not sure. That's okay. Let's move on. Looking for asymptotes, we realize that we have no horizontal asymptotes because we're on a restricted domain. So here, x is not going to positive or negative infinity. X is restricted to the open interval negative pi over 2 to pi over 2. And for vertical asymptotes, we know that would happen where cosine x is equal to 0, since tan x is sine x over cosine x. Well, where does cosine x equal 0 along this interval? Only at the endpoints that aren't in the interval, so only at positive and negative pi over 2. So we're going to have vertical asymptotes at x equals negative and positive pi over 2. So we know that our graph is going through the origin, and our domain is restricted to negative pi over 2 to pi over 2. And we have asymptotes at those two values. Now let's take a look at relative extrema and intervals of increase and decrease. Our first derivative is going to be 2 minus secant square x. We notice that 2 minus secant square x does not exist again where cosine x is equal to 0 because of the denominator here. And those are the same x values we just spoke about, x equals positive and negative pi over 2. So let's see what we have here by setting this equal to 0. We have 2 is equal to secant square x, so 2 is equal to 1 over cosine square x, which means cosine square x is equal to 1/2. And so that says cosine x is equal to positive negative radical 1/2. And notice radical 1/2 is the same as radical 2 over 2, because this is 1 over radical 2, and if we rationalize here, that's radical 2 over 2. So we're saying cosine x is equal to positive or negative radical 2 over 2. That happens when pi over 4 is the reference angle, and we are in quadrants 1 and 4 right now, because we have x going from negative pi over 2 to pi over 2. And so the two solutions we have are x equals positive pi over 4 and negative pi over 4. These are our critical numbers. So we set up our number line, and notice we don't have arrows on both sides of our number line. I'm using a parenthesis here to indicate it's an open interval. You could also use an open circle, either one would be fine, at negative pi over 2 and pi over 2. And then we're putting the markers of negative pi over 4 and pi over 4 on our number line, and we're going to plug into y prime. And remember, y prime is equal to 2 minus secant square x. And so here we could test x equals negative pi over 3. And so y prime of negative pi over 3 is equal to 2 minus secant square of negative pi over 3. That's 2 minus 1 over cosine of negative pi over 3, all of that squared. Cosine of negative pi over 3. We know that cosine of pi over 3 is equal to 1/2, and cosine is positive in quadrant 4. And so we have 1 over a positive 1/2. That's 2. This is 2 minus 2 squared, so that's going to be negative. Here we can take a look at x equals 0. Y prime of 0 is going to be 2 minus secant square of 0. Secant of 0 is equal to 1. That's 1 over cosine of 0, so that's 1. So this is 2 minus 1, and this is going to be positive. And here we have x equals pi over 3, and that's going to be the same computation we have here. Y prime of pi over 3 is going to be 2 minus secant square of pi over 3. That's going to be 2 minus 1 over 1/2 square. So this is going to be negative. That's 2 minus 4, so that's negative, and we're here. So this says our original function y is decreasing, then increasing, then decreasing. So we have a minimum at x equals negative pi over 4, and we have a maximum at x equals pi over 4. And we should find the corresponding y values so that we can plot these on our graph. So let's go back up to the original and plug in positive and negative pi over 4. y of negative pi over 4 is equal to 2 times negative pi over 4 minus tan of negative pi over 4. Tan of negative pi over 4 is negative 1, so this is negative pi over 2 plus 1. Now to plot that, we might want to have an approximation. So remember that pi is about 3.14, so let's approximate that as about 3. So we have negative 3 halves plus 1, so that's approximately negative 1/2. But when I write down my coordinates, I'm going to write the exact y value, negative pi over 2 plus 1. So let me go back down here. This is negative pi over 2 plus 1. Now let's take a look at positive pi over 4. Y of pi over 4 is equal to 2 times pi over 4 minus tan of pi over 4. So that's pi over 2 minus 1. So this is now about 3 halves minus 1, approximately positive 1/2. And so I'm going to put pi over 2 minus 1 as the y coordinate here. And now plotting these 2 points, we're here. So now we said we have a relative minimum at negative pi over 4 and a relative maximum at pi over 4. We know that we have these vertical asymptotes, so the graph must look like this. And now let's check our concavity. It looks from our sketch like x equals 0 would be an inflection point, and that will have concave up before that and concave down after that, but let's go ahead and check. So we said that y prime is equal to 2 minus secant squared x. So y double prime is going to be 0 minus, the 2 comes down, 2 secant x times the derivative of secant x. That's secant x tan x. So this becomes negative 2 secant square x tan x. Now again, we notice this does not exist at x equals positive and negative pi over 2 because we have cosines in our denominator here. And setting this second derivative equal to 0, we realize that we have 2 factors to set equal to 0. We have to set secant squared x equal to 0 and also tan x equal to 0. But notice secant square x can never equal 0 because this is 1 over cosine square x. So this fraction can't ever equal 0, which means if we have any solutions, they come from here, tan x equaling 0. We know this happens when sine x is equal to 0, and in our given interval, that happens at x equals 0. So x equals 0 is going to be what we plot on our number line for y double prime. And so here, we can plug in, for example, x equals negative pi over 4, and here x equals pi over 4. And our second derivative is negative 2 secant square x tan x. So we have y double prime is equal to negative 2 secant square x tan x. And remember that we're just looking at the sign here, so this is a negative. Secant square must be a positive. And so really we just need to plug in tan x and see what sign that is and then complete the computation. So y double prime of negative pi over 4 is going to be a negative times a positive times tan of negative pi over 4, which we know is negative 1. And so this is a positive product. For x equals pi over 4, y double prime of positive pi over 4 is going to be negative here times the positive here, multiplied by tan of pi over 4, which we know is a positive 1. So this is going to be a negative product, and we're here. So what does it say about y prime? It says that y prime is increasing and then decreasing. And about y, this says that y is concave up and then concave down, so that we have an inflection point at x equals 0. And we already know the y-coordinate to go with that is 0. And does that match what we have already? It does. And so this is a sketch of y equals 2x minus tan x. So with curve sketching, the steps are always the same. You just have to take the time to go through each step. And as you can see from the examples here, the graphs can be quite different for different functions. You'll want to be sure to do enough practice problems to master the curve sketching. And this concludes our video on curve sketching.